Welcome to the fourth lecture on mass transfer operations. In this lecture, we will discuss the diffusion mass transfer, in particular to the steady state molecular diffusion under stagnant and laminar flow conditions. Before going to the lecture, let us have small recap on the previous lecture. In the previous lecture, we have considered the Fick's law of diffusions and we have considered steady state diffusion and unsteady state diffusion. In steady state diffusion, we discussed the Fick's first law and the second case we have discussed the Fick's second law, which is applicable for unsteady state diffusion. Now, steady state molecular diffusion in fluids under stagnant and laminar flow conditions. Steady state diffusion through a constant area if we consider, and then we assume that steady state diffusion in the x direction without any chemical reactions in a binary gaseous mixture of species A and B. For one dimensional diffusions of species A, we know the molar flux equations. Na is equal to minus C dAB dYA dx plus Ya n. This is n is the total molar flux is equal to Na plus Nb. Now, separating the variables in these equations, this equation can be expressed as minus dYA divided by Na minus Yan is equal to dx by C dAB. So, this is equation B. Now, for the gaseous mixture at constant pressure and temperature, the concentration and diffusion coefficient dAB are constant and independent of position and composition. Also, all the molar fluxes are constant in equation B. Equation B is minus dYA divided by Na minus Yan is equal to dx C dAB. Therefore, the equation B can be integrated between the two boundary conditions, which is given as follows. At x is equal to x1, Ya would be equal to Ya1. Ya is the mole fractions of component A in the gas phase. At x is equal to x2, Ya would be equal to Ya2. Ya2 is the mole fractions of component 2 in the gas phase. So, 1 indicates the start of diffusion path and 2 indicates the end of the diffusion path. Now, if we integrate equation B with the above boundary conditions, we can get integral Ya1 to Ya2 minus dYA divided by Na minus Yan is equal to integral x1 x2 dx C dAB. Let Na minus Yan would be equal to Z. So, from here we can write minus dYan would be equal to dz and minus dy would be equal to dz by n. So, substituting the values in the above equations, minus dYA, it would be integral z1 to z2 dz by nz would be equal to integral x1 to x2 dx c dAB. So, since Na minus Yan is z, so it is z, and minus dya over here, which is substituted by dz by n. So, it becomes integral z1 to z2 dz by n into z is equal to integral x1 to x2 dx by c dAB. Now, integral z1 to z2 dz by nz equal to integral x1 to x2 dx c dAB can be written as 1 by n into ln z2 minus ln z1 is equal to 1 by c dAB into x2 minus x1, and from that if we rearrange, it would be ln z2 by z1 is equal to n by c dAB x2 minus x1. Now, if we substitute z at z1 and z2, then it would be ln Na minus Ya2 n divided by Na minus Ya1 n would be equal to n by c dAB x2 minus x1. So, it would be ln n Na by n minus Ya2 divided by n into Na by n minus Ya1. If we just multiply both numerator and the denominator by n, it would be like this, the left hand side equation, and the right hand side equation should be Na by c dAB x2 minus x1. Now, if we multiply both sides with Na in this equation, we will obtain Na would be equal to Na by n into c dAB by x2 minus x1 ln Na by n minus Ya2 divided by Na by n minus Ya1. Therefore, after integration with the boundary conditions, the equation for diffusion for the set conditions can be expressed as these relations. So, Na would be equal to Na by n c dAB by x2 minus x1 ln Na by n minus Ya2 divided by Na by n minus Ya1. Now, steady state diffusion through non-diffusing B. For steady state one dimensional diffusion of A through non-diffusing B, NB would be equal to 0 and Na would be equal to constant. Therefore, the Na by n would be equal to Na by Na plus Nb would be equal to 0, since Nb is equal to 0. So, Na by Na plus Nb would be equal to Na by Na would be equal to 1. Hence, equation C becomes Na is equal to c dAB x2 minus x1 ln 1 minus Ya2 by 1 minus Ya1. For an ideal gas, we can write concentration would be equal to total pressure Pt divided by RT. R is the universal gas constant and T is any temperature. For mixture of ideal gases, the mole fractions Ya in the gas phase can be expressed as the partial pressure of that component divided by the total pressure. The equation D can be expressed in terms of the partial pressure as follows: Na would be equal to dAB Pt divided by x2 minus x1 RT ln Pt minus Pa2 divided by Pt minus Pa1. where Pt is the total pressure, Pa1 and Pa2 are the partial pressure of A at point 1 and 2 respectively. For diffusion under turbulent conditions, the flux is usually calculated based on linear driving force. For this purpose, the equation E can be manipulated to rewrite in terms of a linear driving force. Since for binary gas mixture of total pressure Pt, we can write Pt is equal to Pa plus Pb. Pa and Pb are the partial pressure of component A and component B. So that we can write Pt minus Pa2 would be equal to Pb2 and Pt minus Pa1 would be equal to Pb1. Hence, we can write Pa1 minus Pa2 would be equal to Pb2 minus Pa1. Then the equation E can be written as Na would be equal to dAb Pt divided by RT x2 minus x1 into Pa1 minus Pa2 divided by Pb2 minus Pb1 into ln Pb2 by Pb1. So, we can rearrange this relation as Na would be equal to dAb Pt by RT x2 minus x1 Pblm into Pa1 minus Pa2. In this relation, Pblm is the logarithmic mean of partial pressure of species B, which is defined as Pblm is equal to Pb2 minus Pb1 divided by ln Pb2 by Pb1. The component A diffuses by concentration gradients. The gradient is minus dya dx. Here flux is inversely proportional to the distance through which the diffusion occurs and the concentration of the stagnant gas, that is in terms of the logarithmic mean of partial pressures of species B, because with increase in x and Pblm resistance increases and flux decreases. This change of concentration or the partial pressure can be expressed in terms of the simple profiles, which is shown over here. Y axis Pa or Pb in terms of say atmosphere, and x axis is the distance, may be represented by z. So, which varies from 0 0.2, 0.4, 0.6, 0.8 and 1.0, and this partial pressure can vary from So, this is the variation of concentration of Pa 2 to Pa 1. And the concentration variation of Pb can be expressed PB1 so PT is the total pressure which is equal to partial pressure of A plus partial pressure of B. This is the variation of PA and this is the variation of partial pressure of component B. So, A is diffusing through these directions. So, this is the partial pressure distribution of A in non-diffusing B. Now, let us take an example. Carbon dioxide is diffusing through non-diffusing air under steady state conditions at a total pressure of 1 atmosphere and temperature of 300 Kelvin. The partial pressure of carbon dioxide is 20 kilopascal at one point and 5 kilopascal at other point. The distance between the points is 5 centimeter. We need to calculate the flux of carbon dioxide given that at 300 Kelvin and at 1 atmosphere pressure the diffusion coefficient of carbon dioxide in air is equal to 2 into 10 to the power minus 5 meter square per second. Now, let us solve this. We assume that it is ideal gas. Let air be the component V. So, we can write N CO2 would be equal to d CO2 air divided by RT into x2 minus x1 into PT by PBLM into partial pressure of CO2 at 1 and partial pressure minus partial pressure of CO2 at 2. So, this is d CO2 air is given 2 into 10 to the power minus 5 meter square per second at 300 Kelvin and 1 atmosphere pressure. So, that this data is given. Now, P is the total pressure which is 1 atmosphere and if we just convert into kilopascal it would be 101.3 kilopascal which is equal to 1.013 into 10 to the power 5 pascal. Now, temperature is 300 Kelvin which is given, x2 minus x1 the distance of diffusion is 5 centimeter. If we convert to meter it will be 0.05 meter, and then partial pressure of carbon dioxide at point 1 is given 20 kilopascal which is 20,000 pascal. Partial pressure of carbon dioxide at point 2 is 5 kilopascal which is 5000 pascal and R is given as 8314 pascal meter cube per kilomole Kelvin. So, PB1 would be equal to PT minus P carbon dioxide minus at point 1 which would be equal to 101.3 minus 20 kilopascal which is around 81.3 kilopascal, and PB2 we can calculate PT minus P CO2 at point 2 which is equal to 101.3 minus 5 kilopascal which is 96.3 kilopascal. So, this PB1 and PB2 are calculated. Now, if we calculate PBLM log mean partial pressure difference PB2 minus PB1 divided by ln PB2 by PB1, it would be equal to 96.3 minus 81.3 divided by ln 96.3 divided by 81.3 kilopascal which is 88.59 kilopascal and which is equal to 88,590 pascal. Now, we can calculate the flux NCO2 would be equal to 2 into 10 to the power 5 meter square per second into 1.013 into 10 to the power 5 Pascal divided by 8314 Pascal meter cube per kilomole Kelvin into 300 Kelvin is the temperature, and the distance is 0.05 meter into 88590 Pascal, and the pressure differential is 20,000 minus 5,000 Pascal. So, it will lead to 2.75 into 10 to the power minus 6 kilomole per meter square second. Now, steady state equimolar counter diffusion. This is the case for the diffusion of two ideal gases where an equal number of moles of the gases diffusing counter currently to each other. In this case, NB would be equal to minus Na, which is equal to constant, and so from this we can write Na plus Nb is equal to 0. Now, the molar flux in equation A at steady state can be written as, this is equation 1, Na is equal to minus C dAB dy dx plus yan, and Na plus Nb is equal to n, which is 0. So, if we substitute that n is 0, we will get Na is equal to minus C dAB dya dx. Now, for ideal gas, the concentration is equal to per total pressure P T divided by R T. R is the universal gas constant and T is the temperature. So, we can write Na would be equal to minus dAB Pt by RT into dya dx. Now, if we integrate this relation with the boundary conditions at x would be equal to x1 and ya would be ya1 and x is equal to x2, ya would be equal to y2, ya2. The equation of molar diffusion for steady state equimolar counter diffusion can be represented as Na would be equal to dAB Pt by RT x2 minus x1 ya1 minus ya2. So, from here if we rearrange, it would be dAB by RT x2 minus x1 into partial pressure of A1 PA1 minus partial pressure of component 2 at point 2 is PA2. Now, let us consider another examples. Carbon dioxide is diffusing at steady state through a straight tube of 0.5 meter long with an inside diameter of 0.05 meter containing nitrogen at 300 Kelvin and 1 atmosphere pressure. The partial pressure of carbon dioxide at one end is 15 kilopascal and 5 kilopascal at the other end. Given that at 300 Kelvin and 1 atmosphere pressure, the diffusion coefficient is 4 into 10 to the power minus 5 meter square per second. Now, we need to calculate the following for the steady state equimolar counter diffusion: the molar flow rate of carbon dioxide and the molar flow rate of nitrogen, and we need to see whether they are equal or not. So, we assume the ideal gas in equimolar counter diffusion for CO2. So, the flux for CO2 we can write NCO2 would be equal to dCO2 N2 divided by RT x2 minus x1 PCO2 at 1 minus PCO2 at 2. So, the value which are given dCO2 N2 would be equal to 4 into 10 to the power minus 5 meter square per second Pt is the total pressure 1 atmosphere, which is equal to 101.3 kilopascal, which is equal to 1013 into 10 to the power 5 pascal. T is the temperature is 300 Kelvin, and x 2 minus x 1 is the distance of diffusion, which is 0.5 meter. Partial pressure of CO2 at 1 is 15 kilopascal, which is 15,000 pascal, and partial pressure of CO2 at 0.2 is 5 kilopascal, which is 5000 pascal. R is known 8314 pascal meter cube per kilomole Kelvin. So, NCO2, if we substitute these parameters, we will get 4 into 10 to the power minus 5 divided by 8314 into 300 into 0.5 into the partial pressure difference 15,000 minus 5,000. So, it will lead to 3.21 into 10 to the power minus 7 kilomole per meter square second. Now, the molar flow rate of carbon dioxide is equal to NCO2 into the area. A is the cross sectional area of the tube. So, given that internal diameter of the tube is di, which is 0.05 meter. So, cross sectional area of the tube A is equal to pi di square by 4, which is equal to pi by 4 into 0.05 square, which is equal to 1.96 into 10 to the power minus 3 meter square. Now, molar flow rate of carbon dioxide we can calculate, which is equal to 3.21 into 10 to the power minus 7 kilomole per meter square second, which we have calculated flux, into the cross sectional area 1.96 into 10 to the power minus 3 meter square, which will give 6.29 into 10 to the power minus 10 kilomole per second. Now, let us calculate for nitrogen using the similar equations. It is this CO2 N2 by RT x 2 minus x 1 into the partial pressure of N2 at 1 minus partial pressure of N2 at 0.2. So, the data for Pn2 1 is Pt minus Pco2 at 1, which is equal to 101.3 minus 15 kilopascal. So, which is around 83.3 kilopascal. So, which is 86,300 pascal. Pn2 at 2 is equal to Pt minus Pco2 at 2, which is equal to 101.3 minus 5 kilopascal, which is equal to 96.3 kilopascal, which is equal to 96,300 pascal. So, Pn2 at 1 and Pn2 at 2 is known. Now, we know that for equimolar counter diffusion, the diffusion coefficient of d CO2 N2 would be equal to d N2 CO2. Now, if we substitute that, we will obtain the flux is 3 minus 3.21 into 10 to the power minus 7 kilomole per meter square second. So, the molar flow rate we can calculate using similar ways, minus 3.21 into 10 to the power minus 7 kilomole per meter square 7 into meter square second into 1.96 into 10 to the power minus 3 meter square, which would be equal to minus 6.29 into 10 to the power minus 10 kilomole per meter square second. So, this proves that the mutual diffusivities for the flux for both the components for equimolar counter diffusions are same. For non-equimolar counter diffusion, in many situations A and B molecules diffuse in opposite directions at different molar velocities. Like, let us consider the following reactions. We can consider 2A plus B is equal to 2C. So, in this case, when 1 mole of B diffuses towards A and 2 moles of A diffuse in the opposite direction, we can write Na is equal to minus Nb by 2. So, from this we can calculate the flux of different components using these relations. So, thank you for hearing these lectures, and in the next lecture we will discuss on the diffusion mass transfer for non-uniform geometries. Thank you very much.